We start section 2 with a definition, an exponent definition that relates to radicals. And that is for any non-negative real number and any natural number index, natural numbers being the numbers 1, 2, 3, 4, on up to infinity. I can state that a base raised to the fractional power 1 over n power is equal to the nth root of that base. Here's some examples. If I had x to the 1/3 power, I am just asking for the cubed root of x. If I had 5b to the 1/2 power, I am just asking for the square root of 5b. Again, here's my indices, square root. If I had 16 to the 1/4 power, I am just asking for the 4th root of 16, which is actually 2. So, in this direction, I should be able to go in the other direction as well. If I had the 5th root of 3xy, then I am also asking for 3xy raised to the 1/5 power. If I had the cubed root of x cubed y squared, then you need to recognize that I'm just asking for that base, x cubed y squared, or what's under the radical, raised to the 1/3 power. I need you to be able to go in both directions. I need you to be able to take a base raised to a fractional power with 1 in the numerator and recognize that the denominator is the indice. I'm asking for the cubed root of x. I'm asking for the square root of. I'm asking for the 4th root of. Or when I have an index, I can write that radicand raised to the 1/5 power. Again, the radicand here raised to the 1/3 power. You need to be able to go in both directions. Here's another property of exponents. Speaking of which, you should be sure to check, click on the assignments button, and about the 4th or 5th item down says additional material from your instructor, or maybe important additional material from your instructor. Again, click on that, select chapter 6, and look for a summary of exponents and radical expressions to be found there. One of the properties of radical expressions is that if I have a base raised to a fractional power, now no longer 1 over n, but m over n, I can write that as, again, notice this denominator is the indice, the nth root of a to the m power, or the nth root of just a, all of that raised to the m power. And watch what that does for me. It allows me to simplify expressions without using my calculator. If I have 8 to the 2/3 power, I can think of that as the cubed root of 8 squared, that's this form, or I can think of that as the cubed root of 8 raised to the 2nd power. Either of those is useful to me. I'm particularly fond of this way because I recognize that the cubed root of 8 is equal to 2. Because 2 times 2 times 2 is 8. So what I have here is in parentheses, I have the number 2, but I'm being asked to square that. This is equal to 4. If I had looked at it here in this pattern, or this method of representing this expression, I would have had a 64 under the radical, and then I would have been asking myself to take the cubed root of 64. Well, that happens to be the number 4, because 4 times 4 times 4 is 64. Either way, I got the correct answer of 4. You choose which way you like to represent this property in order to simplify the expression. This example right here, I'm asking to take the square root of that 4 to the 5th power. I can think of it as this, which I don't like without a calculator, because 4 to the 5th power is hard for me to do in my head. Now, mind you, you have a calculator. Or I can write this as the square root of 4, all of that raised to the 5th power. That's this version of this property. And the square root of 4 is equal to 2, so I'm asking you to take 2 to the 5th power, and 2 times 2 times 2 times 2 times 2 is 32, and I was able to do it without a calculator. Could have done it here, would have just had to make the calculator do all the work. Some time ago you studied negative exponents. And when you had a base raised to a negative power, you were expected to write it as its reciprocal, 1 over that base raised to the positive power. That's what this property shares with you, but we'll deal with it and use it with radicals. If I have a base raised to the negative m over n power, you need to recognize that that is equal to 1 divided by a to the m over n power. And so my first example is if I have 16 to the negative 1/4 power, I need you to think of that as 1 over 16 to the positive 1/4 power. And then now recognize recognize the first property we used a bit ago, which says that if I'm raising something to the 1/4 power, I am asking for the 4th root of that. Well, the 4th root of 16 is equal to 2, and finally I can simplify this expression and say that that's equal to 1/2. The next example that I might look at is a base of 25 raised to a negative 3/2 power. Again, using the property just before this one. However, first I'm going to rewrite this with a positive exponent. So I need to write this as 1 over that base raised to a positive 3/2 power. And now I'm going to use the property where a base is raised to a fractional power and look at this as the square root of 25 because of that 2. And I like the square root of 25. It's equal to 5, so I'm going to do that, and then I'm going to cube it. Keep my 1 in the numerator. And so I have 1 divided by, again, this is 5, and then I need to cube it, and finally that's equal to 1 over 125. No calculator involved. I need to be able to simplify this expression and represent it as a fraction. If you give me answers on that proctored test as a decimal number, in other words, you go in and let your calculator do all the work, you are going to be marked wrong, and I will not come back and say that that's correct. So if you gave me an answer of whatever 1 divided by 125 is as a decimal number, that will be marked incorrect. It will be asked for as a fraction. I'd like to remind you of some more properties of exponents. They're on the left-hand side, and there's examples representing them. The first one is when you have two bases, like bases, that you're multiplying together, please remember that the rule is to just add their exponents. So if I take x to the second times x to the third, I'm going to get x to the 5th power because 2 plus 3 equals 5. All right, so again, remember, when you multiply, you add. When you divide, we've learned in the past that we subtract. So the answer to this problem is y to the 3rd power because 7 minus 4 is 3. Next, when you raise a power to a power, x to the 2nd raised to the 5th power, the shortcut is to multiply, so I get x to the 10th. Y to the 3rd raised to the 5th power is equal to y to the 15th. Please remember these three properties. We're going to go ahead and use them in this first example. Actually, we're just going to use this multiplication property in the first example and continue with these next two in the examples that follow. So let's say that I asked you to take 6 to the 1/5 power and multiply it by 6 to the 2/3 power. Well, the bases are alike. Sure, I'm asking for the 5th root of 6 times the cubed root of 6 squared, but that's a mess. And so what I need to do is just think about this property right here of multiplication and recognize that if I want to multiply these together, I need to add their exponents. Well, the only way to add those exponents is to get common denominators. So I'm going to work to get a 15 in each of these denominators. So 1 over 5 is going to become 3 over 15. That's the same thing as 1/5. And 2 over 3 is going to become 10 over 15. That's the same as 2/3. I can now go ahead and add their exponents, and I'm going to write this step down, the 3/15 and the 10/15, and finally I'm left with 6 to the 13/15 power, and that's all we'd like to do with that one there. Certainly you could write this as the 15th root of 6 to the 13th power, but we're not expecting that in this section. Here's a division problem where the bases are alike and the exponents are unusual. I know that with division I need to subtract since my bases are alike. So I need to take the 7/6 and subtract the 3/2. Well, I'm not going to do that until I get a common denominator with those fractions. The 7/6 I'm going to leave alone. The 3/2, however, I got to get a denominator of 6. So that's going to be a 2 to the 9/6 power. Again, that's the same as 3/2. And now I'm prepared to go ahead and subtract. So I'll take the 7/6 and subtract the 9/6. That's going to give me 2 to the negative 2 over 6 power. Reduce it before you do anything more. So call that 2 to the negative 1/3 power. And if you'd like, I'm done. But if you'd like, I just want to remind you that I can think of this as, 1 over 2 to the 1/3 power, get rid of the negative exponent, and finally, that is the same thing as 1 over the cubed root of 2. I just want you to be aware that we're working in section 2 of Chapter 6. And I'm doing problems very similar to those in the exercise set under Objective C, where the directions say use the laws of exponents to simplify and write your answers with positive exponents. So let's look at this next problem. I have x to the negative 2/3 power, y to the 1/4 power, and I want to raise all of that to the 1/2 power. Again, you need to remember the property that I shared with you a few slides back, where we said if you have bases, multiple, raised to a power, that the shortcut is to multiply their exponents. So I need to take this negative 2/3 and multiply it by 1/2. I'll go ahead and write that out. So it's going to be a negative 2/3 times 1/2. That's what the exponent of x will be. And the base of y will have an exponent of 1/4 times this 1/4 times this 1/2. And when I clean that up, I'm going to go ahead and notice that these 2's can be reduced. Now, careful, I do have a negative exponent. The 2's will be reduced, and that 2/6 will become 1/3. And this 1/4 times 1/2 is 1/8. And finally, I just need to remember that bases raised to a negative power are not acceptable. They're just not recognized answers. But the y to the 1/8 power stays where it is. This x to the minus 1/3 gets moved downstairs and becomes x to the positive 1/3. That's because I'm writing it as its reciprocal, 1 over x to the positive 1/3 power. This one I didn't have to do that. I left that alone. And if I wanted to, now I don't believe our book is going to expect this of us, but if I wanted to, I need you to remember that this is just the 8th root of y, and this is just the cubed root of x. A couple of examples here. The directions just say to simplify these expressions. Remember all the properties that we've learned. If I want to take the 6th root of x cubed, I can write that as x to the 3/6 power. And then I can simplify that 3/6 to 1/2. And then finally I get to say, oh, that's just the square root of x. I'm done. I've simplified that expression. When I want to take the 6th root of 8, I'm asking to take 8 to the 1/6 power. Geez, how do I simplify that? And the only way I can think is possibly I could take this base of 8 and write it as 2 to the 3rd power. That is equal to 8. And raise this whole expression to the 1/6 power. And now what happens? When raising a power to a power, I get to multiply those exponents. So 3 times 1/6 is 3/6, which is 1/2. And so I get to reduce this whole expression finally. 2 to the 1/2 power is the square root of 2. I was able to reduce this because I was able to think of that 8 as 2 to the 3rd power and then use the property of exponents and simplify. This is an interesting problem, and it ultimately is going to lead me to a shortcut in simplifying radical expressions. I'm going to go ahead and use the properties for exponents. I want to take the 5th root of a to the 10th, b to the 15th, which means I want to take this base, a to the 10th, b to the 15th, and raise it to the 1/5 power. And the property of exponents says to go ahead and multiply those exponents. So I have a to the 10/5 and b to the 15/5 power. When I multiply it, it's 10 times 1/5 is 10/5. 15 times 1/5 is 15/5. Well, that reduces right here to a 2. So I have a to the 2nd power, and 15 divided by 5 here is a 3. And I'm done. I've simplified this. But from here on out, what I'm going to do is when I see under a radical a base raised to some power, and if it's divisible by this, the indice, this 10 divided by 5, I'm going automatically to a squared. And this 15 divided by 5, I'm going automatically to b cubed and simplifying it without writing all these steps. But it's due to these properties of exponents, that allows me to do that. Under Objective D in Section 2, I'm now using the properties of exponents to simplify a radical expression so that it becomes one radical expression. I have here, however, the 4th root of 7 times the square root of 3. This is a tough expression to simplify, but what I have to do is I have to think of it in its exponential form. So what I have here is 7 to the 1/4 power, times 3 to the 1/2 power. And what I'm going to do is I'm going to start thinking about, while the bases are not alike, I cannot multiply this and add their exponents. What I will go ahead and do, however, is get these fractional exponents do have a common denominator. It might help me in raising all of this to the 1/4 power. So now what I'm going to do is I'm going to take, since both of these have a denominator of 4, I'm going to go ahead and say, let's take this whole expression and raise it to the 1/4 power with a 7 to the first power and a 3 to the second power. Again, we're working backwards now. This 1 times 1/4 is that 1/4, and 2 times 1/4 is that 2/4. And I can now write this as the 4th root of this expression in the parentheses, 7 times 3 squared, or 7 times 9, which is 63. And I've written this now as a single expression, having gone from two radicals that had different roots. Another problem, I want to simplify this into a single radical expression. The cubed root of y times the 5th root of 3y. I'm going to write this with fractional exponents, so y to the 1/3 power, and then 3y to the 1/5 power. And it appears as though, this is commonly true, that I can't do anything with this until I get common denominators. So I'm going to write y to the 1/3 as y to the 5/15 power, and the 3y I'm going to write as 3/15. And then finally I'm going to think about getting this whole expression raised to the 1/15 power. And so in order to do that, I need to take this y and raise it to the 5th power, its numerator, because 5 times 1/15 is at 5/15. And the 3y needs to be raised to the 3rd power, because the 3 times 1/15 will give me 3/15. Now I better simplify this before I go and write this as the 15th root of anything. And what I'm going to do is I'm going to bring this in front right here. 3y, that quantity cubed, again, just a way back when, this is what this means. So that's 27y cubed. And then I have this y to the 5th here. And so here in my next step, I'm going to multiply these together because I can. Their bases are like, I'll add their exponents. And so what I will have is 27y to the 8th power, all of this raised to the 1/15th power. And finally, I'm going to write this as the 15th root of 27y to the 8th. I have a single expression, single radical expression. And I have done so by writing these as fractional exponents, getting common denominators, using one of the properties of exponents, and simplifying everything until I get to that last point. This is an interesting problem, and it ultimately leads to one of the properties of radicals, although it's not stated in your book. I want to take the 4th root of the square root of x. So I'm going to first think about the square root of x, what's inside, the innermost, if you will. That's x to the 1/2 power, right here. But then I want to take the 4th root of that. That means raise it to the 1/4 power. Well, the shortcut when taking a base, which is an exponent, and raising it to a power, is to multiply their exponents. Well, 1/2 times 1/4 is 1/8. So what I have here essentially is the 8th root of x. And I'm done, but what I want you to notice is one of the properties of radicals says that if you take the root of some base, that you can take their indices and multiply them. This is an understood 2 here when I take the square root of, and 2 times 4 is 8. I could have done that a lot shorter, but I wanted you to see the properties working for us. This is one of the last even problems in section 2. I've actually taken most of these problems right out of your book, typically even problems. In this problem, I want to take the numerator and divide it by the denominator, and I'm noticing that the bases, the first factor in the numerator and denominator, have like bases, and here as well. And I know that when I divide, I should subtract. Well, I can't take 8/15 and subtract 1/3 until I get a common denominator. So it looks as though a common denominator of 15 is going to work. Now, you know, it's not necessary, and actually I think I will go ahead and leave this alone. I possibly could put that into a denominator of 15 as well, but I'm going to try not bothering because they already have common denominators, and those are the ones that I'm going to subtract. So let's go ahead now. Bases are alike, subtract their exponents. 8/15 minus 5/15 gives me 3/15 as an exponent for x. My exponent for y, 7/5 minus a negative 1/5. I'm going to write this off to the side. 7/5 minus a negative 1/5. Please remember that you're going to add the opposite. So 7/5 plus 1/5 is 8/5. And it happens that this fraction, the base x, is raised to the 3/15 power, can be reduced. Oh, a 3 goes in here once, and a 3 goes in here 5 times. So what I have then is x to the 1/5 power and y to the 8/5 power. So why don't I go ahead and think about raising all of this to the 1/5 power, x and y to the 8th. Again, x is raised to the first power, and 1 times 1/5 is this 1/5. 8 times 1/5 is that 8/5. And finally, I would write this as the 5th root of, because of this fractional exponent here, of x to the first, y to the 8th. That concludes section 2. A lot of work with the properties of exponents that are used to deal with radical expressions. Kind of a challenging chapter, a section, maybe the most challenging of this chapter.